Hello everyone, I'm presenting our paper GAN, a double oracle framework for generative adversarial networks. We look into GAN as two-player game between generator and discriminator. And since pure any may not exist in GAN training, we suffer unstable training in GANs. Hence, Miss Any is a more suitable solution concept, but still the large-scale strategy space of GAN makes it difficult to find Miss Any. Hence, our solution is to adapt the DO framework. First, we introduce a GAN as two-player zero-sum game and the Miss strategy formulation of GAN. Next is the double oracle algorithm. We have two best response oracle for the players. We start with a restricted game, solve it to get the any strategies, compute the player best responses, and add them to the restricted game for the next iteration until termination. With the two background literatures, I'll explain the methodology, the general framework of GAN. We start with a restricted game with two sets of action each for both players and solve the mathematics game. Then we compute the best responses and add the generator discriminator pair to expand the mathematics game. If best responses do not improve results, the procedure is terminated. Next will be how to find the Miss Any for the respective oracles. Since the current restricted mathematics game is a zero-sum game, we can use linear program to compute the Miss Any for the players in a polynomial time. Hence, we use this equation to compute the Miss Any strategy for the generator player to maximize the worst-case expected utility. Similar equation for the discriminator player. However, there is a risk that the arrays of generators and discriminator parameters become intractable. So to make the algorithm practical and scalable, we propose two methods. The first method is mathematics pruning. We set a support set size, prune at least one strategy with the least probability that contributes the least to the player's winning. But this stage needs at least s equal to 10 to converge. Hence, we further reduce both time and space complexity by continual learning. We make it retain the knowledge of previous networks so that the algorithm will converge with even smaller support set. We treat each network as a task while having a distribution over the task to represent the player strategies. However, one drawback of this approach is catastrophic forgetting. So, to remedy the catastrophic forgetting, we use elastic weight consolidation method. We change the generator loss function from non-saturating to saturating and add a penalty function accordingly. Lastly, we provide comprehensive evaluation on the performance of GAN with different GAN architectures baselines such as GAN, DC GAN, SN GAN, and S GAN. We chose the baseline architectures from each branch of the GAN taxonomy. We also use both synthetic and real-world datasets. The results show significant improvements in both subjective qualitative results. Here is for the synthetic dataset and the real-world Lab A dataset. And also the quantitative metrics compared with their respective GAN architectures. We also compare the wall clock running time to show that our DO variants are more efficient. Hence, to conclude my presentation, we made a novel contribution to GANs by adapting the DO framework with a restricted game and best response oracle for generator and discriminator, a linear program, and propose two scalable solutions such as pruning and continual learning. And we also try to apply the GAN approach to the established GAN architectures. And we also present the extensive experiments by using both synthetic datasets and real-world datasets and show significant improvements over the baselines. So this concludes my presentation. Thank you very much for the attention.